Welcome to a peaceful journey across the tranquil landscapes of Earth's most serene environments. As you settle in, allow your mind to wander across the vast, open spaces that characterize our planet's desert regions. In these quiet places, time moves differently, marked not by hours or days, but by the gentle shifting of sand grains and the subtle erosion of ancient stone. The deserts of our world invite us to slow down, to breathe more deeply, and to appreciate the quiet beauty found in seemingly empty spaces. Tonight, we will explore these peaceful landscapes together, venturing across endless dunes and silent plains, discovering the gentle rhythms that have shaped these environments over countless millennia. Deserts occupy nearly 1/3 of our planet's land surface, creating spaces where silence and solitude reign. These are places defined not by absence, but by a different kind of presence, one that speaks in whispers rather than shouts. As we begin our journey, imagine yourself standing at the edge of an endless horizon where the earth meets the sky in a perfect, uninterrupted line. The air is still, the landscape quiet, waiting to reveal its secrets to those patient enough to listen. The formation of desert environments occurs over immensely long periods of geological time, with each desert having its own unique story of creation. Some deserts, like the Sahara in North Africa, formed gradually as climate patterns shifted over thousands of years, transforming once verdant grasslands into the sand seas we know today. The Sahara stretches across 11 countries, covering an area of approximately 9.5 million square kilometers. Within this vast expanse, the landscape varies from rocky hamadas to gravel plains, from stone plateaus to sand seas called ergs. Other deserts came into being through different processes. The Atacama Desert along the Pacific coast of South America formed in the rain shadow of the Andes Mountains. As moisture-laden air moves eastward from the Pacific Ocean, it rises to cross the tall mountain range. This upward movement causes the air to cool, releasing its moisture as precipitation on the western slopes. By the time this air reaches the eastern side of the mountains, it has lost most of its moisture, creating the dry conditions that characterize a rain-shadowed desert. Desert environments are typically classified into 4 main categories, each with its own gentle patterns and characteristics. Subtropical deserts, such as the Sahara and the Arabian Desert, form around the latitudes of 30 degrees north and south. In these regions, global air circulation patterns create zones of high pressure where air descends, warms, and dries, discouraging cloud formation and precipitation. Coastal deserts, like the Namib, along the southwestern coast of Africa, develop where cold ocean currents cool the air passing over them. This cooling effect reduces the air's capacity to hold moisture, resulting in decreased rainfall when this air moves over coastal lands. The Namib Desert extends for approximately 2,000 kilometers along the Atlantic coast, with average annual rainfall varying from just 2 millimeters in the central regions to about 200 millimeters in the outer areas. Rain shadow deserts, as mentioned earlier with the Atacama example, form on the leeward side of mountain ranges. The Great Basin Desert in the United States represents another example of this type, situated in the rain shadow of the Sierra Nevada mountains. Here, average annual precipitation ranges from 170 to 280 millimeters, with higher elevations generally receiving more moisture than lower areas. The fourth category, polar deserts, might seem contradictory at first. Yet the Antarctic and parts of the Arctic qualify as deserts due to their extremely low precipitation levels. In Antarctica, the average annual precipitation equivalent is less than 50 millimeters, making it technically drier than the Sahara in terms of new moisture received. Within these desert landscapes, the composition of sand itself tells a story of patient transformation. Desert sand primarily consists of small particles of quartz and feldspar, minerals that have withstood the test of time, while softer minerals have worn away. Each grain represents the outcome of a process called mechanical weathering, where larger rocks gradually break down into smaller pieces through temperature fluctuations, wind abrasion, and occasional water action. The color of desert sands varies depending on the mineral composition. The familiar golden yellow color, common in many deserts, comes from iron oxide coating the quartz grains. Reddish sands, like those found in parts of the Australian deserts, contain higher concentrations of iron oxide, while whiter sands may consist almost entirely of quartz or gypsum. In White Sands National Park in New Mexico, the dunes consist predominantly of gypsum crystals, creating an expanse of gleaming white that stretches across 275 square kilometers. As we continue our peaceful journey across these quiet landscapes, notice how the wind moves imperceptibly across the surface, causing the lightest sand particles to shift and relocate. This gentle movement represents the beginning of dune formation, a process that occurs with extraordinary patience over extended periods of time. The wind, in its consistent patterns, becomes the sculptor of the desert landscape, creating forms that appear static, but are actually in a state of perpetual, unhurried change. The most recognizable features of many desert landscapes are the dunes, those graceful, undulating formations that embody the desert's quiet nature. Dune formation begins with the simple interaction between wind and sand, a relationship that develops over countless years into the mesmerizing patterns we observe today. As wind moves across a desert surface, it carries fine sand particles in a process known as saltation. These particles bounce along the ground, typically rising no more than a few centimeters before returning to the surface. Upon landing, they may dislodge other particles, creating a gentle cascade effect. When these moving particles encounter an obstacle, even one as small as a stone or a plant, they begin to accumulate. Over time, This accumulation grows into a small mound, which itself becomes a larger obstacle, collecting more and more sand. The wind continues to move sand up the windward side of this growing formation until the grains reach the crest. At this point, the sand cascades down the leeward slope, coming to rest at what geographers call the angle of repose, typically around 30 to 34 degrees for dry sand. This ongoing process creates different types of dunes, each with its own particular characteristics. Barchan dunes form when the wind consistently blows from one direction across areas with limited sand supply. These crescent-shaped dunes develop horns that point downwind, with the steeper slip face on the concave side. A typical Barchan dune might be between 9 and 30 meters tall, while larger examples can reach heights of 100 meters or more. They typically move forward at rates of 3 to 25 meters per year, though this movement is imperceptible to the human eye over short periods. Linear dunes present another common formation, extending in long, straight ridges parallel to the prevailing wind direction. These dunes can reach extraordinary lengths, some in the Sahara and Arabian deserts extend for more than 100 kilometers. Their height typically ranges from 20 to 100 meters, though exceptional examples may reach 200 meters. The Great Sandy Desert in Australia features numerous linear dunes, some extending for over 300 kilometers, with remarkably consistent spacing between them, typically between 0.5 and 3 kilometers apart. Star dunes represent perhaps the most stable of the major dune types. These form in areas where wind directions change frequently, creating a central peak with arms radiating outward in multiple directions. Some of the world's tallest dunes are star dunes, reaching heights of over 300 meters in places like the Grand Erg Oriental in Algeria. Their shape comes from the way sand accumulates from multiple directions, with slip faces developing on several sides. The arms of a star dune typically number between 3 and 6, though examples with more arms do exist in certain locations. Transverse dunes form perpendicular to the prevailing wind direction in areas with abundant sand supply. These create wave-like patterns across the landscape, with the ridges sometimes extending for several kilometers. The distance between successive ridges, known as the wavelength, typically ranges from 50 to 500 meters. In the Badain-Jaran Desert of China, some transverse dune systems support small lakes in the interdune areas, creating unusual oasis environments between the sand ridges. Beyond the dunes themselves, desert landscapes feature a variety of other topographical elements shaped by the patient forces of erosion. Desert pavements form when wind removes finer particles from the surface, leaving behind a layer of closely packed stones or pebbles. These pavements can extend for many square kilometers, creating surfaces that remain remarkably stable over thousands of years. In some regions, notably the Atacama Desert, These stone pavements have remained undisturbed for so long that the exposed surfaces of the rocks have developed desert varnish, a thin, dark coating composed of clay minerals, iron oxide, and manganese oxide. Yardongs represent another distinctive desert landform, created when wind erodes soft, sedimentary rock into long, streamlined ridges parallel to the prevailing wind direction. These features can range from small ridges just a few meters high to massive formations extending for kilometers. In the Lut Desert of Iran, yardongs have been measured with lengths exceeding 40 kilometers and heights reaching 80 meters. Their elongated forms resembling the hulls of ships navigating through a sandy sea. Desert plateaus or mesas form when layers of resistant rock protect underlying softer materials from erosion. As the surrounding areas gradually wear away, these flat-topped elevations remain standing above the surrounding plains. The Colorado Plateau in the southwestern United States provides numerous examples of such features, with mesas extending for many square kilometers at elevations averaging between 1,500 and 2,100 meters above sea level. In regions where water occasionally flows, desert landscapes may feature wadis or arroyos, dry stream beds that carry water only during infrequent rain events. These channels can remain dry for years or even decades between flows. Yet, they play an important role in shaping the desert topography. The Wadi Rum in Jordan extends approximately 110 kilometers in length and reaches widths of up to 60 kilometers in some sections, with its distinctive red sandstone formations rising from the valley floor to heights of 1,750 meters. The movement of sand across desert surfaces occurs with extraordinary slowness under normal conditions. In areas away from active dune fields, individual sand grains might move no more than a few centimeters per year. Even in more active regions, the typical migration rate of dune formations ranges from 1 to 10 meters annually, though rates vary considerably depending on local wind patterns and sand supply. The tallest dunes generally move the slowest, with some large star dunes in the Namib Desert showing movement of less than 1 meter per decade. This patient movement creates a landscape that appears unchanging to the casual observer, yet remains in a state of constant, gentle flux. The North American deserts, for instance, have maintained similar overall appearances for approximately 8,000 to 10,000 years, since the end of the last glacial period, despite the ongoing redistribution of their constituent materials. The Namib Desert, considered by many geographers to be the world's oldest desert, has existed in its current form for at least 55 million years, and possibly as long as 80 million years, with its basic topographical features remaining remarkably consistent throughout this vast expanse of time. As we continue our tranquil journey across Earth's desert landscapes, we can explore the statistical patterns that characterize these environments, beginning with precipitation levels. Deserts are defined primarily by their aridity, with most receiving less than 250 millimeters of rainfall annually. However, this simple threshold conceals a remarkable range of conditions across different desert regions. The Atacama Desert holds the distinction of being the driest non-polar desert on Earth. In its hyperarid core, annual precipitation averages less than 1 millimeter. Some weather stations in the region have never recorded rainfall in over 40 years of observation. The extreme aridity results from a combination of factors, including its position in the rain shadow, influence of offshore, and stable high-pressure systems that discourage cloud formation. By comparison, the Sonoran Desert of the southwestern United States and northwestern Mexico receives between 75 and 380 millimeters of rainfall annually, with the precipitation distributed across two distinct rainy seasons. The winter rains typically arrive between December and March, bringing gentle, prolonged precipitation associated with frontal systems moving inland from the Pacific. The summer monsoon season, from July to September, brings more intense but shorter rainfall events resulting from convective thunderstorms. This biseasonal pattern distinguishes the Sonoran from most other North American deserts and contributes to its relatively rich biodiversity. The Kalahari Desert in southern Africa presents yet another precipitation pattern, with annual rainfall varying from about 110 millimeters in the southwest to approximately 500 millimeters in the northeast. This gradual transition creates subtle shifts in vegetation communities across the region. The precipitation arrives predominantly during the summer months of November through April, with the winter season typically receiving less than 15 millimeters of rainfall. In Australia's Great Victoria Desert, precipitation averages between 200 and 250 millimeters annually, but the timing of this rainfall is notably unpredictable. Years may pass with minimal precipitation, followed by periods of above-average rainfall. This irregularity means that the actual moisture available to desert ecosystems varies significantly from the long-term averages, creating cycles of scarcity and relative abundance that shape both the landscape and its inhabitants. Temperature patterns in desert environments reveal equally interesting statistical relationships. The diurnal temperature range, the difference between daytime highs and nighttime lows, tends to be pronounced in desert regions due to the limited moisture in the air. Water vapor serves as a thermal buffer, absorbing and releasing heat gradually. In its absence, temperatures rise and fall more dramatically within a 24-hour period. In the central Sahara Desert, average daily maximum temperatures during the summer months typically range between 40 and 47 degrees Celsius. During the same period, nighttime temperatures may fall to between 15 and 25 degrees Celsius, creating a diurnal range of approximately 25 degrees. By comparison, tropical rainforest environments might experience a diurnal temperature range of only 5 to 7 degrees Celsius. The coldest deserts present different temperature patterns altogether. The Gobi Desert of Mongolia and northern China experiences average January temperatures between -25 and -13 degrees Celsius in its northern reaches. July temperatures in the same region average between 20 and 25 degrees Celsius, creating an annual temperature range of approximately 45 degrees. This substantial seasonal variation results from the desert's high-latitude continental position, far from the moderating influence of oceans. When examining the relationship between elevation and temperature in desert environments, we observe a general decrease in temperature with increasing elevation, averaging approximately 6.5 degrees Celsius per 1,000 meters of elevation gain. This relationship creates vertical climate zones within desert mountain ranges. The Taibesti Mountains in the Central Sahara illustrate this pattern clearly. At their base, around 500 meters above sea level, average annual temperatures measure approximately 22 degrees Celsius. At the summit of Emi Kusi, the highest peak at 3,445 meters, average annual temperatures drop to about 4 degrees Celsius. Temperature inversions represent another interesting meteorological phenomenon in desert basins. These occur when cooler air becomes trapped beneath warmer air, reversing the normal temperature gradient. In desert environments, inversions frequently develop overnight as the ground rapidly loses heat through radiation. The air in direct contact with the surface cools quickly, while air at slightly higher elevations remains warmer. Death Valley in California often experiences such inversions during winter months, with temperature differences of 8 to 12 degrees Celsius measured between the valley floor and points just 100 meters higher in elevation. Groundwater systems beneath major deserts follow their own statistical patterns. The Nubian sandstone aquifer system underlies portions of Chad, Egypt, Libya, and Sudan, covering approximately 2.2 million square kilometers. This ancient water reservoir contains an estimated 150,000 cubic kilometers of groundwater, most of which accumulated during wetter periods between 10,000 and 25,000 years ago. Carbon-14 dating indicates that some of this water has remained underground for more than 40,000 years, making it a truly fossil resource disconnected from the current hydrological cycle. The thickness of this aquifer varies considerably across its extent, ranging from just a few meters near its edges to more than 3,500 meters in certain basins. The depth to the water table similarly varies, from areas where groundwater naturally reaches the surface as springs to regions where it lies more than 1,200 meters below the desert floor. Recharge rates, the amount of new water entering the system, average less than 1 millimeter per year across most of the aquifer's extent, illustrating the exceedingly slow pace of desert hydrological processes. Similar groundwater systems exist beneath other major deserts. The Great Artesian Basin, underlying portions of Australia's interior, covers approximately 1.7 million square kilometers and contains an estimated 64,900 cubic kilometers of water. In some areas, this water remains under sufficient pressure to rise naturally to the surface when wells are drilled. Though this phenomenon has diminished over time, as water withdrawal has reduced the overall pressure within the system. Let us now examine the gentle elevation patterns found across some of the world's desert plateaus. The Colorado Plateau of the southwestern United States covers approximately 337,000 square kilometers and maintains an average elevation between 1,500 and 2,100 meters above sea level. Within this broad average, numerous individual plateaus create a complex topography. The Kaibab Plateau, north of the Grand Canyon, reaches elevations of 2,800 meters. The Aquarius Plateau in south-central Utah averages about 3,000 meters in elevation across its 2,300 square kilometer surface. The Markagunt Plateau, also in southern Utah, rises to approximately 2,900 meters at its highest points, while its general surface maintains elevations between 2,400 and 2,700 meters. In North Africa, the Tademate Plateau in central Algeria covers roughly 110,000 square kilometers at an average elevation of 500 meters. Its remarkably flat surface varies by no more than 100 meters in elevation across most of its extent. To the southeast, the Tassili Enager Plateau reaches somewhat higher, with elevations averaging 1,500 meters across its approximately 72,000 square kilometer area. Further east, the Gilf Kebir Plateau in southwestern Egypt covers about 7,770 square kilometers at elevations ranging from 300 to 600 meters above the surrounding desert floor. The Tibetan Plateau represents the world's highest desert plateau, covering approximately 2.5 million square kilometers at an average elevation of 4,500 meters above sea level. Though not entirely desert, its northern portions receive less than 100 millimeters of precipitation annually, qualifying them as true desert environments. The Chang Tang region in the northern plateau averages about 4,800 meters in elevation across its 700,000 square kilometer extent, with local variations rarely exceeding 200 meters from this average, a remarkable consistency across such a vast area. Within Australia's desert regions, the Barkly Tableland covers approximately 283,000 square kilometers at an average elevation of 250 meters. The surface of this plateau varies by less than 100 meters across most of its extent, creating an remarkably level landscape. To the west, the Hammersley Range presents a more varied plateau landscape, with elevations ranging from 450 to 1,250 meters across its 80,000 square kilometer area. As we observe these statistical patterns and relationships within desert environments, we begin to appreciate the subtle interconnections that characterize these seemingly simple landscapes. The relationship between precipitation, temperature, elevation, and groundwater creates a complex system that evolves with extraordinary slowness, each element influencing the others in a delicate balance maintained over geological timescales. The climate patterns of desert environments develop through the interplay of multiple atmospheric and geographical factors, creating conditions characterized by aridity and often extreme temperature fluctuations. The diurnal temperature cycle, the daily pattern of warming and cooling, represents one of the most consistent features of desert climates worldwide. This cycle begins each day as the sun rises and solar radiation reaches the desert surface. With minimal cloud cover to filter this incoming energy, the ground warms rapidly during the morning hours. The rate of temperature increase typically averages between 5 and 8 degrees Celsius per hour during the first 4 hours after sunrise in many warm deserts. By midday, surface temperatures often exceed air temperatures by 30 to 40 degrees Celsius, with dark rock surfaces in places like Death Valley occasionally reaching 80 degrees Celsius during summer months. As this surface heating intensifies, the air immediately above the ground warms through conduction and begins to rise through convection. This process continues throughout the daylight hours, with maximum air temperatures typically occurring between 2 and 4 in the afternoon, rather than at solar noon. The delay results from the cumulative heating of the air column over several hours of intense solar radiation. With sunset, the temperature pattern reverses. Without cloud cover to trap heat, the desert surface radiates energy rapidly back to the atmosphere and beyond to space. During the first 2 hours after sunset, temperatures typically decrease by 5 to 10 degrees Celsius. This cooling continues throughout the night, with the minimum temperature usually occurring just before sunrise. The total diurnal temperature range, the difference between daily maximum and minimum temperatures, averages between 15 and 25 degrees Celsius in most warm deserts, though extreme ranges exceeding 30 degrees have been recorded in particularly arid regions. This daily pattern shows remarkable consistency throughout the year in low-latitude deserts near the equator, where seasonal variations remain minimal. In the Arabian Rub al-Khali, or empty quarter, for instance, the diurnal temperature range averages about 20 degrees Celsius in both January and July, though the absolute temperatures differ between seasons. The January diurnal cycle might range from 12 to 32 degrees, while the July cycle might span from 25 to 45 degrees Celsius. In mid-latitude deserts, seasonal variations modify this daily pattern significantly. The Gobi Desert experiences average daily maximum temperatures of approximately 0 degrees Celsius in January, with minimums averaging minus 20 degrees Celsius. By July, maximum temperatures average 32 degrees Celsius, with minimums around 15 degrees. Despite these seasonal differences, the fundamental pattern of rapid daytime heating and nighttime cooling persists year-round. The seasonal climate patterns of desert regions vary considerably depending on geographical location and surrounding topography. In the northern hemisphere subtropical deserts, such as the Sahara, summer temperatures reach their peak in July and August, with average daily maximums exceeding 40 degrees Celsius across much of the region. Winter brings cooler conditions, with January averages typically ranging between 15 and 25 degrees Celsius during the day, falling to between 5 and 15 degrees at night. Precipitation patterns show equal variability across different desert regions. The Sonoran Desert's biseasonal rainfall pattern, mentioned earlier, contrasts with the single rainy season experienced in the Sahel region along the southern margin of the Sahara. There, approximately 90% of annual precipitation falls between July and September, coinciding with the northward movement of the intertropical convergence zone. Annual totals range from about 200 millimeters at the desert's edge to approximately 600 millimeters in the southernmost portions of the Sahel, with this gradient occurring over a distance of 300 to 400 kilometers. The Namib Desert along Africa's southwestern coast experiences a different pattern altogether, with coastal areas receiving most of their moisture not as rainfall, but as fog. This fog develops when the cold Benguela current cools the air immediately above the ocean's surface below its dew point. Prevailing winds then carry this moist air inland, where it condenses as fog against the desert slopes. These fog events occur between 60 and 200 days annually, providing critical moisture to desert organisms despite annual rainfall totals of less than 25 millimeters in many locations. Occasional rainfall in desert environments follows patterns distinctly different from those in more humid regions. When precipitation does occur, it often arrives in brief, intense events. In the Sonoran Desert, approximately 30 to 40% of annual rainfall typically falls during the 3 most intense rainfall events of the year. These concentrated precipitation episodes can deliver substantial amounts of water in very short periods. Rainfall rates exceeding 100 millimeters per hour have been recorded during desert thunderstorms, though such intensities rarely last more than 15 to 20 minutes. The effectiveness of this precipitation varies seasonally. Summer rainfall in hot deserts often evaporates quickly, with potential evaporation rates exceeding 10 millimeters per day. Studies in the Mojave Desert indicate that up to 75% of summer rainfall may return to the atmosphere through evaporation within 24 hours of a precipitation event. Winter rainfall, arriving when temperatures and evaporation rates are lower, tends to penetrate more deeply into the soil profile, with 40 to 60% remaining available for plant uptake or groundwater recharge. Wind patterns across open desert landscapes follow their own rhythms and cycles. In many desert regions, the daily heating and cooling cycle generates predictable local wind patterns. During daylight hours, as the desert surface warms, air rises through convection and is replaced by air flowing in from surrounding areas, creating daytime winds that typically reach their maximum velocity in mid-afternoon. Average wind speeds during this period range from 15 to 25 kilometers per hour in many desert regions, though considerably higher velocities may occur during storm events. At night, the pattern typically reverses. As the desert surface cools rapidly after sunset, the air immediately above it also cools and becomes denser. This cooler, denser air flows downslope in areas with topographic relief, creating gentle katabatic winds that average between 5 and 15 kilometers per hour. In enclosed basins, this downslope movement can create pools of cool air that contribute to the temperature inversions mentioned earlier. Seasonal wind patterns overlay these daily cycles. In the Sahara Desert, the harmattan wind blows from the northeast between November and March, carrying fine dust particles southwestward toward the Gulf of Guinea. Average wind speeds during harmattan conditions range between 20 and 40 kilometers per hour, with gusts occasionally exceeding 60 kilometers per hour. During particularly strong harmattan events, visibility may reduce to less than 1 kilometer due to suspended dust. Humidity levels in desert environments typically remain quite low, though they follow discernible patterns throughout the day and across seasons. In the Central Sahara, relative humidity averages between 10 and 15% during afternoon hours throughout much of the year. During nighttime hours, as temperatures fall, relative humidity typically increases to between 25 and 35%, despite no addition of moisture to the air. This change results solely from the temperature dependence of relative humidity measurements. Seasonal variations in atmospheric moisture content remain minimal in most desert regions. In the Atacama Desert, average water vapor content in the atmosphere measures approximately 2 grams per cubic meter throughout the year, with variations rarely exceeding 0.5 grams in either direction. For comparison, tropical rainforest environments typically contain 25 to 30 grams of water vapor per cubic meter, while mid-latitude temperate regions show seasonal variations between approximately 5 and 15 grams per cubic meter. This consistent aridity contributes to the extraordinary clarity of desert skies. With minimal water vapor to scatter light, visibility often extends to the horizon, limited only by the curvature of the earth and any dust suspended in the atmosphere. Studies in the Negev desert have documented visibility exceeding 80 kilometers on approximately 40% of days throughout the year, with this percentage rising to over 60% during winter months, when dust storms occur less frequently. The interplay between these various climate elements, temperature, precipitation, wind, and humidity, creates the distinctive conditions that characterize desert environments. These patterns, while harsh by human standards, have remained remarkably consistent over extended periods, allowing for the evolution of highly specialized adaptations among desert organisms and the development of unique geomorphological features across desert landscapes. Human adaptation to desert environments represents a fascinating chapter in our species' relationship with challenging landscapes. Throughout history, communities have developed ingenious techniques for securing water, perhaps the most fundamental necessity for desert survival. Traditional water harvesting systems reflect deep understanding of local conditions and extraordinary patience in working with minimal resources. In the Negev desert of Israel, archaeological evidence reveals sophisticated water management systems dating back approximately 2,000 years. The Nabatean civilization constructed networks of small dams and channels that directed runoff from occasional rainfall into cisterns carved from the underlying bedrock. These cisterns typically held between 20 and 150 cubic meters of water, with the largest examples reaching capacities of 300 cubic meters. The harvested water served both domestic and agricultural purposes, supporting communities in a region that receives between 80 and 150 millimeters of annual rainfall. Similar technologies developed independently in North Africa, where fagaras or qanats, gently sloping underground tunnels, tapped groundwater sources and transported the water to settlement areas through gravity flow. These remarkable systems sometimes extended for many kilometers, with the longest examples in Iran measuring over 50 kilometers from source to outlet. The underground design minimized evaporation losses in the arid climate, with water temperature typically remaining between 15 and 20 degrees Celsius throughout the year, regardless of surface conditions. The construction and maintenance of these water systems required enormous community effort. A typical 15-kilometer fagara might include between 60 and 100 vertical access shafts, each reaching depths of 10 to 50 meters below the surface. Historical records indicate that maintaining such systems occupied approximately 15 to 20% of adult labor in traditional desert communities, highlighting the central importance of water management in these environments. Population density across major desert regions varies considerably, but remains generally low compared to global averages. The Sahara Desert, covering approximately 9.2 million square kilometers, supports a permanent population of about 4 million people, creating an average density of 0.43 persons per square kilometer. Within this average, considerable local variation exists. Oasis communities along the Nile Valley reach densities exceeding 1,000 persons per square kilometer, while vast expanses of the Central Sahara remain essentially uninhabited, with densities below 0.1 persons per square kilometer across areas exceeding 100,000 square kilometers. The population of Australia's desert regions presents similar patterns. The country's arid zone covers approximately 3.5 million square kilometers and supports a permanent population of about 180,000 people, creating an average density of 0.05 persons per square kilometer. Indigenous communities have maintained a presence in these landscapes for at least 50,000 years, developing sophisticated knowledge of water sources and food resources that allowed for sustainable occupation of seemingly inhospitable terrain. Across the southwestern United States, the population of desert regions has increased substantially during the past century, largely through immigration rather than natural increase. The combined metropolitan areas of Phoenix, Tucson, Las Vegas, and Albuquerque now support approximately 7.5 million residents in landscapes receiving less than 300 millimeters of annual rainfall. This growth has relied heavily on extensive water infrastructure, including dams, aqueducts, and groundwater pumping systems that transport water from distant sources or extract it from non-renewable underground reserves. Traditional architectural adaptations to desert environments reveal sophisticated understanding of passive temperature regulation. In North African and Middle Eastern desert settlements, buildings typically feature thick walls constructed from mud brick or stone, materials with high thermal mass that moderate temperature fluctuations. These walls, often measuring between 40 and 80 centimeters in thickness, absorb heat slowly during daylight hours and release it gradually during the cooler night, creating interior spaces that typically vary by no more than 5 to 8 degrees Celsius throughout the diurnal cycle. Courtyard designs feature prominently in traditional desert architecture across multiple cultures. These enclosed outdoor spaces create microclimates through a combination of shade, evaporative cooling, and air circulation. Studies of traditional courtyard homes in Morocco have documented temperature differences of 10 to 15 degrees Celsius between the interior courtyard and surrounding streets during summer midday hours. The courtyard's proportions typically maintain a specific relationship between width and height, with ratios between 1:1 and 2:1, providing optimal shade throughout most of the day. Window placement in traditional desert dwellings reflects careful consideration of solar angles and prevailing wind directions. in two-story structures. Upper-level windows often measure between 20 and 30% smaller than those at ground level, reducing solar gain while still providing adequate light and ventilation. The positioning of windows on opposite walls creates cross-ventilation patterns that help maintain air movement despite low average wind speeds. Desert communities have also developed distinctive social adaptations to their environments. Daily activity patterns in traditional desert societies typically include a midday period of reduced physical exertion during the hottest hours, with more intensive activities scheduled for morning and evening hours when temperatures moderate. This pattern remains evident in the business hours observed across much of the Middle East and North Africa, where many establishments close for several hours during midday before reopening in the late afternoon and remaining open into the evening hours. Seasonal migration represents another traditional adaptation to desert conditions. Bedouin communities in the Arabian Peninsula historically moved between different elevations and landscapes throughout the year, following seasonal patterns of water availability and vegetation growth. These migrations typically covered distances of 100 to 300 kilometers annually, with specific routes determined by rainfall patterns in any given year. Similar practices developed among desert peoples in North Africa, Central Asia, and Australia, demonstrating convergent adaptation to similar environmental challenges across widely separated regions. Dietary adaptations among desert peoples emphasize foods with high water content and those that can be stored for extended periods without spoilage. Date palms, cultivated in desert oases for at least 5,000 years, produce fruit containing approximately 20 to 30% water and 60 to 70% sugars by weight. A mature date palm typically yields between 40 and 80 kilograms of dates annually, providing a concentrated source of calories that remains edible for many months without special storage requirements. Traditional varieties number in the thousands, with distinct types selected for different qualities, including sugar content, storage durability, and ripening time. Animal husbandry in desert regions focuses on species adapted to arid conditions. Domesticated camels require watering only every 7 to 10 days when feeding on dry forage and can tolerate water losses of up to 25% of their body weight without ill effects, a remarkable adaptation compared to most mammals, which experience severe physiological stress with water losses exceeding 10 to 15%. Sheep and goats raised in desert environments typically require watering every 2 to 3 days, with certain desert-adapted breeds developing physiological mechanisms that reduce water loss through respiration and excretion. These animals convert sparse vegetation into protein sources that complement plant-based foods in traditional desert diets. Clothing adaptations in desert cultures balance the seemingly contradictory needs for cooling and protection from solar radiation. Traditional garments typically cover most of the body with loosely woven fabrics in light colors, creating an insulating layer of air between cloth and skin. The Tuareg people of the Central Sahara traditionally wear indigo-dyed cotton veils and robes that cover almost the entire body, with the fabric's loose weave allowing air circulation while providing protection from sun and blowing sand. Similar principles inform traditional clothing from the Arabian Peninsula to the Thar Desert of India and Pakistan, demonstrating convergent solutions to shared environmental challenges. Transportation networks across desert landscapes have evolved from ancient caravan routes to modern highways, though the fundamental challenges of distance and exposure remain. Traditional camel caravans typically traveled between 25 and 40 kilometers per day, with major trans-Saharan routes requiring 40 to 70 days to complete. These journeys followed carefully mapped paths between water sources, with distances between wells typically ranging from 1 to 5 days travel. Major caravan cities developed at strategic points where routes converged, creating trading centers that connected desert regions with the wider world. Modern desert highways often follow these ancient routes, taking advantage of topographical features that have guided travel for centuries. The construction of these roadways presents unique engineering challenges related to temperature extremes, with asphalt surfaces in some regions experiencing annual temperature variations exceeding 80 degrees Celsius between winter nights and summer days. Specialized pavement mixtures incorporating polymer modifications help prevent softening during extreme heat, while foundation layers typically extend 50 to 80 centimeters below the surface to provide stability in shifting sand environments. Settlement patterns in desert regions show remarkable continuity over time, with contemporary population centers often occupying the same locations as ancient communities. This persistence reflects the fundamental constraints of water availability and agricultural potential, which remain relatively stable despite technological advances. In Egypt's western desert, the major oases, Bahariya, Farafra, Dakhla, and Karga, have supported continuous human occupation for at least 8,000 years, with archaeological evidence indicating similar population distributions throughout this extended period. The economic activities that sustain desert communities have diversified considerably in modern times, though traditional practices persist in many regions. Pastoralism continues to support approximately 22 million people across the arid regions of Africa and the Middle East, with annual livestock movements following seasonal patterns established over centuries. These pastoral systems typically operate within rainfall zones, receiving between 100 and 400 millimeters annually. Areas generally considered marginal for crop production, but capable of supporting grazing animals when managed appropriately. Oasis agriculture represents another traditional economic adaptation to desert environments. These intensively cultivated areas typically utilize irrigation water from springs, shallow groundwater, or occasional surface flows to support multi-layered production systems. A traditional date palm oasis in Morocco or Algeria might include 3 cultivation tiers: date palms forming the upper canopy at heights of 15 to 30 meters, fruit trees like apricot, pomegranate, and olive in the middle layer at 3 to 10 meters, and annual vegetables, herbs, and grains at ground level. This arrangement maximizes productivity within limited space while creating beneficial microclimate effects through shade and reduced evaporation. Contemporary economic development in desert regions increasingly focuses on sectors less dependent on local water resources, including mining, energy production, tourism, and specialized manufacturing. The Atacama Desert in Chile now supports a significant mining industry focused on copper and lithium extraction, with mining operations consuming approximately 0.9 cubic meters of water per second, a substantial demand in an environment receiving less than 10 millimeters of annual rainfall. This water comes primarily from groundwater sources, supplemented increasingly by desalination plants along the Pacific coast. Solar energy production represents a growing economic activity well suited to desert environments. The southwestern United States hosts several large-scale solar installations, including facilities in the Mojave Desert that generate more than 2,000 megawatts of electricity. These installations typically occupy between 5 and 10 hectares of land per megawatt of capacity, creating a new form of land use in previously undeveloped desert landscapes. Similar developments are underway across North Africa, the Middle East, and Australia's arid interior, taking advantage of the reliable solar resources characteristic of desert regions. Tourism has emerged as another significant economic activity in many desert areas. The Grand Canyon in the southwestern United States attracts approximately 6 million visitors annually, while Monument Valley receives about 350,000 visitors in a typical year. In Egypt, the pyramids and archaeological sites along the Nile Valley draw millions of international visitors, creating employment opportunities in regions where traditional agricultural and pastoral activities face increasing challenges due to climate change and water scarcity. Land use patterns across desert regions vary considerably depending on local conditions and development histories. The Arabian Peninsula presents a particularly interesting case study in rapid transformation. The United Arab Emirates has converted approximately 4% of its land area to urban uses since 1975, creating cities with population densities ranging from 3,000 to 15,000 persons per square kilometer in areas that previously supported fewer than 5 persons per square kilometer. This development has relied on imported water supplied through desalination, with the country's plants producing approximately 8 million cubic meters of fresh water daily from seawater, a process requiring substantial energy inputs. The future of human occupation in desert landscapes faces both challenges and opportunities related to climate change, technological innovation, and evolving economic systems. Climate models predict increasing temperatures across most desert regions, with average increases of 2 to 4 degrees Celsius projected for the period between 2050 and 2100. These changes will likely intensify the fundamental challenges of desert habitation, particularly regarding water resources and agricultural productivity. Adaptation strategies currently under development include improved water harvesting techniques, drought-resistant crop varieties, and more efficient irrigation systems. Traditional knowledge often informs these innovations, with ancient water management approaches being reevaluated and modified for contemporary conditions. In Morocco's Atlas Mountains, rehabilitated Qattara systems, similar to the Fagaras mentioned earlier, now provide water for both traditional oasis agriculture and newer commercial operations, demonstrating the continuing relevance of indigenous technologies. As we conclude our journey across Earth's desert landscapes, we might reflect on the remarkable balance these environments represent. Places where extremes of heat and aridity create challenges that have inspired both natural and human adaptations of extraordinary sophistication. The subtle beauty of these quiet landscapes reveals itself to those willing to observe with patience, appreciating the delicate relationships that sustain life in seemingly inhospitable terrain. The vast dune fields stretching toward distant horizons, the ancient watercourses etched into stone landscapes, the surprisingly diverse communities of plants and animals that have made these harsh environments their home, all remind us of the resilience inherent in natural systems and human societies that have learned to live within environmental constraints. As our journey ends, perhaps we carry with us a deeper appreciation for these serene desert landscapes, where silence and space invite contemplation, and the passage of time is measured not in moments, but in millennia. As the stars emerge in the clear desert night sky, our journey across Earth's quiet dunes comes to a gentle conclusion. The patient processes that shape these landscapes continue without pause. The imperceptible movement of sand grains, the slow weathering of stone surfaces, the gradual shifts in climate patterns that unfold across centuries and millennia. Desert horizons extend not only across space, but also through time, connecting past and future in landscapes where change occurs with extraordinary deliberation. The human communities that have made these challenging environments their home demonstrate similar patience, developing cultural adaptations refined over countless generations. Their traditional knowledge reflects deep understanding of desert rhythms and resources, offering valuable perspectives as contemporary societies seek sustainable relationships with arid landscapes. As you drift toward sleep, perhaps you carry with you images of endless dune fields, catching the golden light of sunset, ancient wadis winding between weathered stone formations, or star-filled skies arching over silent landscapes. These quiet desert scenes invite us to slow our own pace, to breathe more deeply, and to appreciate the subtle beauty found in seemingly empty spaces. In this peaceful awareness, we find rest, like desert travelers throughout history who have paused their journeys as darkness falls, knowing that morning will bring another day of gentle discovery across Earth's tranquil desert horizons.